All right, pre-calc today in section 3.3, we are going to review quadratic functions and their properties. None of this really should be new. This was all covered in Algebra 2, but it's been a while, so let's make sure that we're comfortable again with quadratics. So a lot of objectives for the day. We're going to graph quadratics using transformations, which I may or may not do actually. We'll take a look at how things are transformed, but I think I want to focus more on just how to graph one in general. And then identify the vertex and axis of symmetry, graph a quadratic function using its vertex, axis, and intercepts, find a quadratic function given its vertex and one other point, and then find a maximum or a minimum value of a quadratic function. So let's get into it. A definition. So a quadratic function is a function in the form y equals, or f of x equals a times x squared plus b times x plus c, where a, b, and c are real numbers, and a cannot equal 0. Okay, the domain of a quadratic function is going to be all real numbers. All right, because if you see something that looks like, what a quadratic looks like is it looks like a parabola shape, right? So it looks either like this or like this. All right, so the domain, the possible x values, this will just keep going, to infinity eventually, very slower and slower as it increases, because it's going to get steeper and steeper, but it will go to infinity in the x direction in both ways. So the domain will always be all reals. Okay, so that's the definition of a quadratic. Let's get right into graphing one of these. So quadratics are, like I said, parabolas, and notice that they could either open up or down. Remember that this term vertex refers to either the high point or the low point of the graph, depending on if it opens up or down. So if it opens up, it's the low point. If it opens down, it's the high point. Right, that is the vertex. And notice that the axis of symmetry will always go through the vertex. Axis of symmetry, symmetry means, things are mirrored the same on either side. So if you have an axis of symmetry through the parabola, we know that the distance on either side is always going to stay consistent of that on that either side of that line of axis of symmetry. So the axis of symmetry, again, is a line that goes right through the middle of a parabola. All right, and notice that it always goes through the vertex. That's important. So axis of symmetry always goes through a vertex. Okay, so the vertical line passing through the vertex, again, known as the axis of symmetry. And once we know one point on this parabola on either side of the axis of symmetry, we know another point, because it's the same distance throughout. If we're talking about this point right here, it's the same exact distance as it is on the other side of the axis of symmetry to this point over here. That becomes more important later. Okay, so the axis of symmetry and the vertex, how do we find it? You might remember that the axis of symmetry equation is found, and notice it'll always be an x equals because it'll be a vertical line, right? So vertical lines are x equals type of equation, so it'll be x equals negative b over 2a. And where do the a and the b come from? Well, they come from our standard form of a quadratic equation. So we could remember that y is equal to ax squared plus bx plus c. So the b and the a values come from right here. So if they give us the equation, that's where we get our a and our b from. Now sometimes we rearrange this. Okay, and as we explore this further, this will begin to make a little bit more sense. But we can rearrange this into another form called the vertex form. If things are in the vertex form, it looks like this. Okay, so I can rewrite any quadratic equation into the vertex form of that equation. So I can manipulate it to make it look like this, where h, okay, and k, h and k, are the vertex. So if I had something that looked like this, y is equal to 2 times x minus 3 squared plus 4, my vertex is going to always be whatever makes this guy go to 0. Remember, this is a negative here, right? So whatever makes this go to 0, and then this guy. So the vertex in this particular one that I just made up would be 3, 4. So vertex form is nice because we can look at the equation and we can see what the vertex is. Up here, however, if we have things in this form, we cannot tell what the vertex is unless we plug it into, unless we plug things into this axis of symmetry and solve for y, which I will show you how to do. All right, so example 1 says graph a quadratic function using transformations. Maybe let's not use the transformations quite yet. Okay, so let's just graph this thing. To graph this, what I want to do is I want to find where the vertex is, and then I also want to find the axis of symmetry. I'm actually going to start with axis of symmetry. All right, so this is not in vertex form, so I could show you how to put it into vertex form, but for now, let's not worry about that. Let's just find our axis of symmetry. So we know that x is equal to negative b over 2a. Here, we can identify that a is 2 and b is 8. So we have x is equal to negative 8 over 2 times 2, which is equal to negative 8 over 4, which is equal to negative 2. All right, so I know that my x value of my vertex, my axis of symmetry, is equal to negative 2. So just so that we get a clear picture of what's going on. Okay, if my axis of symmetry is here at negative 2, that means that the parabola is going to be the same on either side of that line. That also means that the x value of my vertex, because the vertex can be anywhere on this line, right, is going to also be negative 2. So I know that my x value of my vertex is negative 2. And how I find where my vertex is, well, I know since my x value is negative 2, I can plug that back in here and see what my y value is. And the only point that should work there is going to be the vertex, because the vertex always lies on the axis of symmetry. So I'm going to plug it in. 2 times negative 2 squared plus 8 times negative 2 plus 5. All right, so negative 2 squared is 4. 4 times 2 is 8. 8 plus 8 times negative 2 is negative 16 plus 5. So 8 minus 16 is negative 8. Negative 8 plus 5 is equal to negative 3. All right, so assuming that I didn't make any mistakes there, my vertex lies on negative 2, negative 3. There's my vertex. Now, something that we haven't talked about yet, but something that should intuitively make sense to you, is that if the lead term is positive, we know that this thing's going to open up. All right. The other thing that we haven't talked about is where the y-intercept would be. Well, remember, you guys, that the y-intercept always happens when x is equal to 0. So if x is equal to 0, then I know if we plug a 0 in there, we know that this would go away, and we'd be left with 5. So at 0, 5, we have the y-intercept. All right, so now that we know the y-intercept, what I can do is, notice I know this distance as well, right? This distance is 2 over to that 5, so I can go a distance of 2 in the other way, because this is an axis of symmetry. And we have this parabola shape. Okay, so it opens up, it has a vertex of negative 2, negative 3, and we know that it has this crossing here on the y-axis at 5. All right, so for example 1, this is really all they want. But if you remember, if you go back to Algebra 2 and you remember what we did here and what we paid close attention to when we were doing these quadratics, and what we will eventually do is we want to know where exactly this thing crosses the x-axis. And in this particular case, we know that it happens in 2 different locations, but it's hard to tell exactly where that is based on this graph. So if you go back to your Algebra 2 roots, you'll remember that we used to factor to find those. So we're going to bring factoring back. for the purposes of this lesson, we will probably just go straight to the quadratic equation, which I've taught you guys in years past. So we'll talk about all that here in a minute. All right, so there's our picture. Okay, got our graph, found the vertex, found the axis of symmetry. Okay, now, part 2, objective 2, is how to identify the vertex and axis of symmetry of a quadratic function. Okay, I actually kind of already went over that, but let's just do it again. So again, to find the axis of symmetry, we're going to take negative b over 2a. Then we're going to take that value, whatever we get for this thing, and we're going to plug it back in for x, because that will tell me where I am on the y at that location. And that xy coordinate, you guys, is the vertex. The vertex is always negative b over 2a, and then taking that and plugging it in for the function. So notice they just, to show that, they said f of negative b over 2a, right? Where you take this x value that you get from here and you plug it back into the function. All right, it won't be a negative b over 2a, it'll be some number that you're going to plug back in for x to get the y value out. And we know that the parabola opens up if our first term is bigger than 0, if our a term is bigger than 0, and it will open down if it's less than 0. All right, so here we go. Example 2, locating the vertex without graphing. All right, we can do that. We did it already in the first example. So to locate this, we are going to plug it into x equals negative b over 2a. All right, so when I plug it in, my x value here is, my b value here is 8. Okay, so I have, this is a, this is b, this is c. Okay, so I have negative 8 over 2 times negative 2. This is the same thing as negative 8 over negative 4, which last I checked was 2. Okay, so I know that my axis of symmetry happens at 2. I also know that that is my x-coordinate of my vertex. Now, I'm going to take that and plug it back in. So negative 2 times 2 squared plus 8 times 2 minus 3. I plugged it back into the equation, and I get negative 8 plus 16 minus 3. Negative 8 plus 16 is 8. 8 minus 3 is 5. So the vertex for example 2 will be at 2, 5. All right, let's keep cruising. That's how we find the vertex without graphing something. Now objective 3 says to graph a quadratic function using its vertex, its axis, and its intercepts. So now is when we're going to bring in the factoring portion of things. All right, so the x-intercepts of a quadratic function. This is not necessary to remember per se. It could be handy, but it's not fully necessary. But if you remember the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, we studied that in depth in Algebra 2. What is inside of the radical is known as the discriminant. All right, so we know that if that thing is bigger than 0, that it will have 2 distinct x-intercepts. If it's equal to 0, it will have 1 intercept. That means that the graph will look something like this, where it comes down and touches the x-intercept. And if it's less than 0, there will be none. Okay, so that would be like this example here, where I have the graph that's sitting above or below and will never cross the x. Okay, so that's the discriminant. You'll see why it's not that crucial, because you'll be able to use your quadratic function and tell that actually when you do the full process out. So example 3 says how to graph a quadratic function by hand using its properties. Okay, so they want us to graph this using its properties, and then they want us to determine the domain and the range, and determine where f is increasing and where it is decreasing. So step 1, is this thing opening up or is this thing opening down? Well, the first term here, the a term, x on the x squared, is negative. Therefore, I know this is opening down. Okay, so I'm going to get a picture that looks like this. I don't know how it's opening down. That could be moving around later, but at least I have a visual. For step 2, we're going to determine the vertex and axis of symmetry of the graph. So let me rewrite it here. Negative 2x squared plus 4x plus 2. All right, so what I want to do here is I want to find the vertex. To find the vertex, I'm going to do my negative b over 2a equals x. Okay, so b in this case is 4, so I have negative 4 over 2 times negative 2. This is a, this is b, okay, which is negative 4 over negative 4, which equals 1. So I know that my vertex, the x value of my vertex is at 1. If I plug a 1 back in, so I'm going to plug that back in there. Negative 2 times 1 squared plus 4 times 1 plus 2. When I do this, I get negative 2 times 1, which is negative 2, plus 4 plus 2. Negative 2 plus 2, that goes away, and I'm left with 4. So at 1 comma 4, I have my vertex. Okay, so now what I know is at 1, 4, I have a vertex. This is my line of symmetry at 1, and I know that it's opening down. Now, how wide it opens, that I don't know necessarily, although I do know that it crosses at positive 2, because that's my y-intercept. Okay, but I don't know exactly where it crosses the x. So step 3 is determining that. The y-intercept that we already know about is if we plug in a 0 for x. So if we have y is equal to negative 2x squared plus, I'm just rewriting it here, plus 4x plus 2. If I plug zeros in for x, that'll be my y-intercept, so I know that that happens at 2, because this will go away, this will go away. The harder one is to see what happens when I set y to equal 0. So if I said y equals 0, I would say 0 is equal to negative 2x squared plus 4x plus 2. Now, I'm not going to get into all the factoring methods. I'm just going to use the universal one for this lesson. Okay, but if you remember your factoring lessons, you can use those. But let's just go into the universal one, which is the quadratic equation. So, again, for review, that is negative b plus or minus the square root of b squared minus 4ac over 2a. All right, where this is a, this is b, this is c. Let's change colors here now and go ahead and plug that stuff in. So negative b would be negative 4 plus or minus the square root of 4 squared, which is 16, minus 4 times negative 2 times 2 all over 2 times negative 2. All right, so let's simplify that a little bit. So I'm going to move, I guess I didn't give myself enough room. I'm going to move this information here and keep going. So we have negative 4 plus or minus the square root of 16 minus 4 times negative 2 times 2. So 4 times negative 2 is negative 8 times 2 is negative 16. Okay, so I have 16 minus negative 16, which is the square root of 32. All right, and that's all going to be over negative 4. All right, so to figure this out, what I have to do is on my calculator, I have to take the square root of 32. Okay, so then this will equal negative 4 plus or minus. If I take the square root of 32 on my calculator, I get 5.656. So we could just round that. Let's just round that to 5. We'll go 5.7 over negative 4. Okay, so if I do negative 5 plus 5.7, sorry, negative 4 plus 5.7, so 5.7, if I add that to negative 4, I get 1.7, so it would be 1.7 over negative 4. Okay, and then for my other one, I'm going to plug it in here, and I get, and by the way, this is approximately divided by 4, negative 0.42. If they are particular about rounding here, you guys, you're going to want to keep the numbers in your calculator so that there's no rounding error. So if you did that, I think you would get negative 0.41. And then for the other one, negative 4 minus 5.7. So On my calculator, I'm taking -4, subtracting 5.7, which should be -9.7, and then I'm going to divide by 4 negative, and I get 2.42. So if I do -4 minus 5.7 over -4, I get 2.42. It's actually 2.4, it looks like it might even be 3. But again, there's rounding error because I rounded this guy. So if you keep that number in your calculator, you won't have the rounding error, and you'll probably get 2.41 or something like that. Okay, so approximately this thing is crossing at -0.4. So if this is -1, it's crossing here, and then at 2.4, which is somewhere in here. We know that the vertex is at 1, 4. So 1, 4 is up here, and now I can, and I know it goes through 2, right? So now I can connect these dots and get a picture, in an accurate picture, and I can actually label those places where those x-intercepts happen. Okay, so that's example 3. Example 4 says graphing a quadratic function using its vertex, its axis, and its intercepts. So first of all, it says graph this function by determining whether the graph opens up or down and by finding its vertex, axis with symmetry, y-intercepts, and x-intercepts, if any. Really, guys, this is no different than the thing that I just did. So I'm going to do it quickly, but I don't want to take up too much time. So let's do example 4 here. So let's find the vertex. So -b over 2a, x is equal to -b over 2a. -b is actually +6 here, because -6 is +6, over 2 times 1, because there's nothing in front of the x squared, so we assume that it is a 1. So in this case here, we are left with 6 divided by 2, which is 3. Okay, so I know my vertex happens at 3. Now I got to plug it back in to see exactly where it happens on the y. So 3 squared is 9 minus 6 times 3 plus 9. Okay, so 9 minus 6 times 3 is 18, so 9 minus 18 is -9. -9 plus 9 is 0, right? So this is equal to 0. So at 3, 0, we have a vertex. All right, that's interesting. So at 3, 0, there's a vertex, and I know it opens up, right? And I know that it crosses the y-intercept at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're right in there. So we have something that looks like this. Okay, and then obviously on the other side, same deal with this line of symmetry. Okay, so it says determine the y-intercept, which we did, and then the x-intercept. Well, this is easy now to understand that if it's touching the x-axis, that is the x-intercept. So the vertex is the only x-intercept. Okay, so the x-intercept is the same as the vertex, 3, 0. The domain and the range of this function, the domain is going to be all reals. The range of this function is going to be the y values where y is greater than or equal to 0, right? Because it starts at 0 and it goes upward. It will never go below the x-axis. And then it says determine where f is increasing and where it is decreasing. So I'll change colors for this. This function starts increasing at the vertex going this way, right? So going on the x, it's going to the right of the vertex. So this is going to increase on the interval of 3, not including 3, to infinity. Okay, and then it's going to be decreasing. So this is increasing. Decreasing from negative infinity to 3. And I don't believe we include the 3 on that, because technically that is not a place where it is increasing or decreasing. So in interval notation, there you go, increasing, decreasing. All right. Oh, but look at this. Here they did include the 3 for both. All right, so since they're showing that here, I would say on your homework, include the 3. Even though technically, on a technical level, I don't believe that it is increasing or decreasing at 3. in particular. So we would go right up to 3, but not really include it. But they're including it here, so I'm going to tell you to include it on your homework. And if you question that, or if you're having issues with that on the homework on the math platform, just check their example and see how they do it on the actual homework. But looks like they're including it here. Okay, so that's example 3, I believe, or objective 3. Objective 4 is to find a quadratic function given its vertex in another point. So here we're going to bring in the vertex form of a quadratic. And I know this is a lot to review and a lot to remember, but you'll want to get this into your notes. So if I have a vertex in another point, it's easiest to plug things into the vertex form of a quadratic, which is this guy. All right, so if they give me something, like here it says the vertex is -3, -7, and the y-intercept is 2. I guess I had the solution in there. What you're going to want to do is you're going to want to start with the vertex form of the equation. Y is equal to a times x minus h squared plus k. All right, so I'm going to plug in the vertex now for h comma k. This vertex is h comma k. All right. So for this one, I'm going to say, okay, y is equal to a times x minus h would be x plus 3 squared, and then I have k is a -7, so minus 7. Okay, that is my equation so far, but they're going to want us to come up with an a for this thing. So in order to come up with that a, I can use the fact that I know the y-intercept. All right, so when x is 0, I know that my y is 2. So I can say this, look. 2 is equal to a times 0 plus 3 squared minus 7. All right, let's simplify this a little bit. This is 2 equals a times 9 minus 7. All right, so let's move some terms here. Let's add 7 to both sides. So we can get the a term by itself. We get 9 is equal to, I'm just going to rewrite this as 9a. All right, so a then is equal to 1. All right, so I can replace that a with 1. So my final answer would be y is equal to 1 times x plus 3 squared minus 7. Okay, if they wanted us to write that in like the other form, I can just simplify it now. And just remember that if you simplify this, x plus 3 squared is the same as x plus 3 times x plus 3, which is x squared plus 3x plus 3x plus 9, or x squared plus 6x plus 9. Okay, and then you have to subtract 7 from that. And so your final answer then would be y is equal to x squared plus 6x, and then 9 minus 7 is just simply 2. Okay, or they might want you to put that in f of x form. Anyway, so that's that one. Oh, and look at that. We got the right answer. That's good. Okay, so objective 5 is the last thing, you guys. It just says determine if the function has a minimum or a maximum. This is actually very simple. If the a term is positive, we know it's opening up. If it's opening up, the function has a minimum. If the a value is negative, it would open down, and the function would have a max. Okay, so looking at this one, I know that this one's opening up. All right, so it's going to have a minimum, and then they want us to know what they want us to determine what the minimum value is. Well, that's just the vertex. All right, so this is just another way of saying what's the vertex, and then identify it as a minimum or a max. Okay, so to find the vertex of this, again, negative b over 2a is going to be 6 over 2, which equals 3. That's my x coordinate. Plug it back in, and I get 9 minus 18 minus 3. 9 minus 18 is negative 9, minus 3 is negative 12. So the minimum value of this quadratic is 3 comma negative 12. And you can check yourself using Desmos or something like that. You can just plug this in. You can look at the minimum and make sure that you're doing your math right if you want to check yourself as you go. All right, guys. That's all. There's a nice summary here, and I believe I have that in your notes someplace. definitely have some good notes on this stuff as it's been a while, and we'll see you guys